Why hello friends! Welcome back to Math Mondays! Oh yeah! Alright, so in this episode we're gonna finish talking about waves. Woo! Waves! Yeah! That wasn't a wave at all, but that's okay. So I started talking high level about waves and the wave equation, like what properties do waves have to abide by? What sort of things are they bound to? And usually the answer to that question is conservation principles, like you cannot create or destroy energy or matter or charge, things like that. So the wave equation is basically a mathematical way for us to translate conservation principles into an equation. And so what I wanted to talk about in this episode was a generic form for an equation that allows us to draw all different types of waves. So this is what the equation looks like. You have the left side that says y, which is a function that depends on x and t. X is space, and t is time. And so y of x and t equals a naught, which is a with a little zero next to it, times sine of k times x minus omega times t. So let's focus on the left side of the equation first. So basically, if you ask what is y, that's a great question. But the first thing that we would have to determine is what type of wave are we talking about? If we're talking about a water wave, then y would be the height of the wave at a given point in space and in time. So for example, if we were a surfer and these water waves were going past us at a constant rate, let's say they look like that, and I wanted to know if I was 20 feet from the shoreline at a given time, how high would I be from equilibrium? Or basically, if there were no waves and it was a calm ocean, how high would I be? So y tells us basically information about the wave as it relates to a specific point in time. Okay, so the other thing I'll mention is that this is a one-dimensional wave. So we can tell that because there's only one variable in space. What would our left side of the equation look like if we wanted to talk about all three dimensions? Oh my gosh. Okay, there we go. That was my attempt at the time waiting soundtrack thing. So basically the left side would look like this. Y is now a function of x. Y, which I guess is kind of weird. So we'll change this to like, I don't know, alpha, just to not repeat ourselves here. Z and t. So now all of a sudden we have three space variables. So x is usually longitudinal, y is typically vertical, and z is depth. Then we also have time, right? Because we exist in 4 dimensions, 3 space and 1 in time. Although it's a little tricky for us because we can't really control t, unfortunately. And then also, if you were going to add the extra 2 spatial dimensions, you would have additional terms on this side of the equation to reflect that. They would all be absorbed, effectively, they would all be absorbed into here. Okay, so that is the left side of the equation. This is basically how we are going to understand how our wave moves in space and in time. And on the right side of the equation is what the wave is actually doing. So effectively what happens is we plug in values for x and t, and we solve for y so that we can know where our wave is, or probably where we are. So let's talk about the right side. A naught is the amplitude of our wave. So in this case, whoops. So the amplitude typically corresponds to both the height and the depth. So it's not exactly to scale, but this, the maximum value, is a naught. And the minimum value is also a naught, although it's negative a naught. So the magnitude of the amplitude is this. So we can like grow our wave by increasing the amplitude, and we can also shrink our wave. So if I wanted a bigger amplitude with everything else the same, you get something like that. And that happens simply by changing this number. Similarly, you can get a smaller wave, just like that, by making this smaller. Okay, so then we get into this function. Sine is just a function that repeats over time. And so then we're most interested in these two values in here. So k is called the wave number. K equals 2 pi divided by the wavelength. So as the wavelength gets bigger, k gets smaller because the wavelength is on the bottom of the fraction. So you can think about like dividing by a bigger number means that the whole value of this gets smaller. The wavelength is the distance between two of the same point on the wave. So for example, if we're going to talk about the two peaks of our wave, the distance between the two in space is the wavelength. It doesn't have to be the peaks. It can be any two of the same point on the graph. So after the wave peaks and it hits the equilibrium state, we could also say that the distance between those two is the wavelength, and the distance between the two troughs is the wavelength. They're all the same. Cool. So that is the wave number. And omega is the angular frequency, which equals 2 pi times the frequency. Boom. If you prefer period of the wave, it would just be 2 pi over t, which stands for the period. So basically you'll notice there's a factor of 2 pi in both of these. My best guess for why we use the wave number and the angular frequency is so we don't have to write as many terms. It's a lot easier to just write k and omega than to keep dragging that factor of 2 pi around. If I were to draw my wave, I would have to actually change my axes to show you the frequency because we want to plot it now in terms of time. It is going to look the same because waves are symmetric, but now the distance in time between two of the same point on the wave is the frequency. So basically, if you're like, I still don't understand wavelength and frequency, wavelength is the amount of space that the wave takes up, sort of, and frequency is how fast the wave is moving. So hopefully that helps clarify. Please let me know if you have any questions or if any of that doesn't make sense. So this is the general form, and you can adjust the different parameters of your wave or how it looks like and how it moves over time by changing the amplitude, the wave number, and the frequency, the angular frequency. Or I guess, well, if you change the frequency, you're going to change the angular frequency because they're related, proportional. You can represent any wave that repeats in time with this equation. Now you might be asking, you're like, I know a little bit about this. Why are you not using cosine? Good question. Basically, cosine functions in very much the same way. You could replace sine with cosine. The only difference is that cosine starts at 1 and it looks like that. So if your wave starts kind of mid amplitude, then you would want to go with cosine. If your wave starts at equilibrium, you can go with sine. Okay, so my video is almost 10 minutes, so I will forego a solution to this problem. Unless you are super curious about it, please leave me a question in the comments and I'd be happy to run through it. The math problem I was thinking about doing is how do you solve for either a position or a time. So for example, if you were a surfer, and you wanted to time your surfing at the peak of the wave, or when y equals a naught, when y is the maximum amplitude of your wave, when in time would you need to go? So actually, I think I would like to give that to you as homework. So you can solve that in a generic form. You don't need any numbers. That's the secret of physics, is they usually will put in the numbers at the very last step. So just tell me in a general form how you would go about finding when a surfer would launch onto the surfboard when the wave is at a maximum. Okay, hopefully I phrased that in a way that makes sense. You're like, what? So yeah, please feel free to ask for clarification. Or if you have any questions about what I have talked about here, please leave your questions and other comments in the comments below. And then of course, this series is for y'all. I love math and I want to share my love of math with everyone else. And so to do that, it helps to tackle problems that you are interested in. So please let me know if there are any topics you're super curious about, or if you have a math problem that is plaguing you in real life that you would like to run through with me together. All right, thanks very much for watching and we'll see you next time. Bye!